In this last section of the course, we're going to look at some of the other models that we can deal with using calculus. We're going to look at some exponential models, we're going to look at some trig models, and we're going to work with them a little bit and find out our big ideas, if you will. We're going to start, say, with the exponential model. We want a nonlinear function. Okay, if it's growing, that means we have some sort of base to an exponent, maybe like 2 to the x, to experience growth. Or we could have some sort of decay, maybe it's a fraction to an exponent that will get smaller over time. Okay. The nice thing about these functions is they don't really have turning points or maximums and minimums, but they do have all the other parts and pieces. Before we start looking at them in depth, we're going to look at a new idea. So I have an example here I want us to try. And I want us to try to evaluate this expression for different values of n. So for instance, if n is 1, we would have the expression 1 plus 1 over 1 to the power of 1. Or in other words, 2 to the 1 comes out to 2. So this is an exponential equation. It's got a base with an unknown exponent, and I want to see what happens as I start changing that base and the exponent. So what if we do n being 2? Well, then we have 1.5 squared, which comes out to 2.5. So I changed my base, I doubled it, but it didn't really change the resulting answer very much. How about if we make that base bigger, or the n value bigger? 1/5 to the 5, so in other words 1.2 to the 5 into our calculators, we should get 2.4883 dot dot dot. It's going to keep on going, okay? Okay, so again, we more than doubled it, but our increase was not very big. Try the power of 10 here. You should get 5937 dot dot dot. Okay, so a little bit of growth. Let's make it a bigger number. Let's go by a factor of 10, up to 100 now. If we try the same equation with 100, it grows, but not very much. Went from like 2.6 to 2.7. If we try 1,000, we'll get just a very, very small change now, right? It seems like as our base, our n value got bigger, our resulting value is actually leveling off. If you try 1,000,000, 2.718. If you think of the biggest number you can possibly think of, like infinity, or the biggest number your calculator can handle, and try that one, you should get 2.7182 dot dot dot. A very small difference. Basically, we reached the end behavior, if you will. We reached the limit of this value. Now, this number that we've been approaching, 2.7182 dot 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 dot, is actually a very special number when it comes to exponential things. Okay, this value, which I'm going to approximate as 2.718, is this special function. We call it e to the x. And that's a button on your calculator. Try and find it. Figure out what e to the 1 is. If you do, it should come out to this number. 2.7182 dot 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 dot. Okay. E is a special number. It represents continuous growth, as opposed to doubling or tripling or quadrupling a value. This is growth that is constantly changing, constantly growing. Okay. We also call it the natural number, or, based on the person who discovered it, Euler's number. Okay. And it's found by doing the end behavior, the horizontal asymptote of this equation. That's what E represents. As I said, we call it constant growth. Okay. Like other exponential functions, for instance, 2 to the x, okay, it has an inverse. When we dealt with exponential functions, we talked about the new inverse, the new idea called a logarithm. Log 2 of x is the inverse of 2 to the x. It undoes an expression. Okay. When we talk about e to the x, it has its own special logarithm. We call it log e of x, okay, where e is your base, or more commonly, ln x. Okay, we call this a natural log. It's a button on your calculator. Try and find the ln button. Pretty sure it should be close to the e button. And it follows all the logarithmic rules. So do you remember how logarithms work? Is going to be one of our questions here. So let's say I had this. I want to figure what it equals. You might remember logarithms are 2 to the power of x. 2 to the power of this comes out to 16. Comes out to that. What's our value that makes that happen? 4. Okay. Lns work the same way. And we'll apply all those same rules. Okay. We'll come across some examples down the road where we will deal with this, okay? One of our basic operations we could do, or basic applications we could do with logarithms, or lns and e's, is continuous growth, finance. Last year we learned about this equation, how to find compound interest based on compounding periods. That's what K stands for, compounding periods. So you calculate interest at the end of a month, or the end of a week, or the end of a year. Well, with exponential functions, you don't have it, it never ends. It's continuous growth. So we have a slightly different version. Our present value times e, continuous growth, with your rate as a decimal, r, and n is your number of years. So we can see how that works, how that can affect our answers. So we're going to look at an investment of $1,000 for 10 years at 5%. Our future value would then be, based on our old stuff, $1,000 I want to grow at 4% compounded quarterly. Oh, sorry, 5%. 5% compounded quarterly, 4 times a year for 10 years. We said it's often easier to put this in your calculator as 5 over 400 to the 40, or change it right to the decimal and do it that way. If you do, you should end up with an answer of approximately 1643.62. Okay, that $1,000 growing by making calculations at the end of each 3-month period. Or, part B here, if we do it monthly, we calculate more often, our money will grow faster. Not a huge amount faster, but a little bit. So now we're going to do it monthly, so compound 12 times a year for 10 years. Or, if you will, 1 plus 5 over 1,200 to the 120. If you do that, you should end up with 1647.01. So, calculate more often, grew a little faster. Or, with our new idea, continuous growth, our future value is still that 1,000, but we're going to use E to represent continuous growth. At 5%, so 0.05, for 10 years. Or, to use your calculator a little bit easier, put that in. And your result in 1648. So not a huge change from this answer. But remember, you're not actually doing anything. You're just making the calculation more often, right? It's not like you're changing the money, changing the time. You're just doing more calculations. And really, the computer's going to be doing that for you. Okay. Now, we want to take this E idea and use it in a calculus format. In other words, we want to be able to find the optimal solutions to problems, right? Maximums and minimums and all that good stuff. Well, to do that, we need derivatives. Now, the nice thing about e to the x, or maybe even the weird thing about e to the x, is for this function, it's its own derivative. So if I had y equals e to the x, then y prime is e to the x. It's a constantly changing derivative. That seems pretty easy, right? Oh, I got my answer off the bat. Now that, unfortunately, isn't always the case. If my e has its own exponent, then the derivative is itself times the derivative of the exponent. So how does that work? Well, let's look at some examples here. So I want to find my derivative. I've got e to an exponent. So when I do that, my derivative is itself times the derivative of the exponent. The derivative of the exponent is just 4. We often write this as 4e to the 4x. Put your number out front. Okay, try some more. Try b here. Yes, e to an exponent. So I write it out itself times the derivative of the exponent. That's 12x. So the better version of this answer we write is 12x e to the 6x squared. We can combine ideas. If we look at c, you might notice that we have two halves to this function that both involve an x. We've got this part, and we've got this part. That's a product rule question. So when I do my derivative, I've got to do my product rule. Derivative of the first part times the second part plus the second part, so there's an e times the exponent times the first part. Now the nice thing about these kind of questions, like other product rule questions, is we can common factor. They have things that are in common. They're both divisible by 2, they both have an x in them, and they both have an e to the 5x in them. So if we take all of that out, we're left with, from the first half, 2, the second half of 5x. And there's the derivative of an e to the x function using the product rule. We'll try some more, see what you guys can do here. Look at letter D. D's got a coefficient out front. When that happens, my derivative keeps the coefficient out front. Okay, I'm going to times it by itself. Then take the derivative of the exponent. Derivative of the exponent itself is 3. I'm going to simplify them up on the 6 with the 3 and making 18e 3x plus 8. Okay, let's try E. E is a messy question because it's not in a very nice format, so let's fix it. Let's call it 4x minus 11 to the 1/2. Then my derivative will be, well, itself times the derivative of the exponent. So I'm looking at just this part now. Derivative of that is 1/2. My base subtracts 1. Is the derivative of the base, which is 4. I'm going to simplify that by multiplying the half and the 4 together. It gives me a 2. So I'll have 2e 4x minus 11 to the 1/2. And because this section has a negative exponent on it, I can put it on the bottom. Make my exponent back to the positive. Okay, notice that in this fraction, this part is the bottom of a fraction, this part's an exponent still. So they don't cancel or anything like that, okay? And last one, let's try F. F looks like a quotient rule question. So if I take the derivative of the first piece times the second piece minus the derivative of the second piece times the first piece over the second piece squared. Okay, like product rule, we can simplify a common factor, 3x squared, and an e to the 6x. Okay, on the first piece, I'll have a 2x. On the second piece, I have just the number minus 1. On the bottom, I'll have an x to the 6. We can cancel 2 of those with 2 of these. Left with 3e6x 2x minus 1 over x to the 4. And so those are some derivatives that we can do using e's, that special exponential function. And what else can we do with this we've been doing along the way? Well, we can talk about tangents. The tangent to the curve. And y equals e to the 4x, and x is 1. Well, e to the 4x is a constantly growing curve. And if I want to find a tangent along the way, I need 2 things. I need a slope and a point. Well, our point is made up of 1 and something. Right? Well, let's figure out that something. We put it into the original equation. 4 times 1, I get e to the 4, which is a big, long, never-ending decimal. So in this case, when we're dealing with e's, we like to keep it exact. E to the 4 is my y value. I also need a slope, an IROC. Our slope is y prime. Well, that's e to the 4x times 4. Or in other words, 4 e to the 4x. I want specifically the derivative at 1. So 4e to the 4 times 1. Well, that, again, is something we want to keep exact. E is a number, but if I turn it into a decimal, it's a never-ending decimal. Right, so I try and keep them exact when I can. All right, our objective is make a line. A line needs a slope. The slope we figured out was that. x plus b. To find a point, or to need a point, there's my point. Y is e to the 4. When x is 1, let's solve this. So on the right-hand side here, we're going to multiply it together. We'll just get 4e to the 4 still. I want to solve for b, so I'm going to rearrange and collect like terms. This is like 1e to the negative 4, or sorry, 1e to the 4 minus 4e to the negative 4, or in other words, negative 3e to the 4. Okay, my equation then is y equals m, which was 4e to the 4, x plus b. Here's my b. And I've got an exact answer for the tangent to the curve at that point, without ever having to worry about the decimals. Unfortunately, the decimals are messy because they're never ending. Okay, last thing I want to talk about today, just get us warmed up with this E thing, is I want to be able to solve some problems. Well, to be able to solve problems involving E, which is an exponential function, I need to go back to basic exponential functions and think how we solve those. So for instance, maybe we had an equation where we had this, and I wanted to solve that. Well, we said way back when, to solve these, I could take the log of each side. And if I did that, I could rewrite it as log 2, bring my exponent down, x log 5, and then solve log 2 over log 5. Well, the same thing is true for e's. Except for instead of using logs, I'm going to use lns to solve these problems. Again, the button on your calculator. Just one nice thing to point out for you. Okay, if you come across ln e, it equals 1. And the reason why is this is the log of base e of e. Well, what to the power e to the power of what equals e? Well, it's always 1. Okay, we just don't usually write log e, we would call that ln, right? Okay, so let's take a look at an example. The distance in meters fallen by a skydiver t seconds after jumping is given by this equation. Determine the velocity. Well, we know velocity is derivative, so we got to take the derivative of this function. But before I do that, I'm going to make this easier. I don't like when things are inside and outside brackets. I think it's easier to multiply it in to make a simpler function to deal with. Now, if I do that, I get that function. Okay, that's my displacement, my distance fallen. So when I go take my derivative now, my derivative, sorry, not v prime, just v. Derivative of 42 is 40. Derivative of 160 is gone. The derivative of the other part is, well, itself times the derivative of the exponent. Remember that negative t over 4 is the same as saying negative 1/4 t, right? So its derivative is just that piece. I'm going to simplify this a little bit just to make it easier. That times this is minus 40e negative t over 4. Here's my derivative. Here's my velocity. Okay, part B, find the terminal velocity of the skydiver by determining the horizontal asymptote. And just for reference, terminal velocity refers to the constant velocity attained. So in other words, it only goes to a certain speed. It will get faster and faster and faster. And we know for horizontal asymptotes, there's a way using calculus of identifying these. Our horizontal asymptote equals the limit of my function as we approach infinity. Well, let's see what happens. If I were to put infinity in for t, negative infinity divided by 4 is basically, well, you can't really divide infinity by 4, right? Still infinity. And negative exponents we know really mean that we should move our base to the bottom. E, which is a number to infinity, is a really, really, really big number. Basically infinity. And 40 divided by infinity is really basically a really small number. Or in other words, we just get 40. The terminal velocity of somebody jumping on that airplane is 40 meters a second. It's as fast as they approach. Now, part C, what time is the velocity 95% of the terminal velocity, and how far have they fallen? Okay, well, let's figure out what's 95% of terminal velocity. Oh, that's 38. I want to know when I hit 38 meters a second. 38 equals, that's my speed, right? So I'm going to take my velocity equation and make it equal. And I want to solve this. Okay, to solve this, I'm going to think of it as an exponential problem. To solve an exponential problem, like we showed up here at the top with the green stuff, I want one base on each side. That's how I want to solve this. Okay, so we're going to do the same thing here. We're going to rearrange this so that I end up with just one base on each side. So I got -2, it's -40. I'm going to divide out the -40, which is going to be positive 0.05. And now I'm going to use my log idea. I got one base on each side, so I'm going to take the log of it, except I've got e's. So I'm actually going to use this natural log. And when we take logs, our exponent can come down in front. And I've just come across something kind of nice. What do we know about ln e? We know that equals 1. So when I'm going to do this with my calculator now, I can type in ln of 0.5, or I can bring the 4 up and then type it in. And hopefully I get a negative value, because I have a -t. And if I get rid of that negative value, I hope you end up with 11.98. It takes 11.98 seconds to reach 95% of terminal velocity. The second part of that question asks us, how far have they fallen? In other words, what is their displacement at 11.98? So if we go back to our very first equation, then I'm going to use the simplified version. We're going to put in t being 11.98. Okay, so 40 times 11.98 minus 160 minus 160e to the negative 11.98 over 4. Let's try to plus 160. Okay, put it on your calculator and hopefully you can get the same answer I did, that they've fallen 327.3 meters. So today's lesson, that's it. We were looking at this letter E, how we can use its derivatives, how we can solve some simple problems involving E, tangents, how we keep them exact. Okay, a couple of questions you should try for homework just to make sure you can do some things with E. We're going to move on. We're going to problem solve tomorrow with E, so we kind of want to be comfortable with it. If you're stuck with this, come see me.